Hello, 7th grade math. Please have your books open to page 283 so you can follow along with our lesson here today. And as you can see on page 283, we are discussing rational numbers. And rational numbers, just to kind of give you a little bit of a sneak peek already right away, rational numbers are really any number that can be written in A over B form. And B cannot be equal to 0. That's really the big thing, is that B cannot be equal to 0. And we'll discuss this a little bit more. I know I'm just kind of saying it right now. But the reason why we want it to be able to be in A over B form is because really what we're doing is we're looking for the fact that rational numbers, hidden in the word rational numbers, is the term ratio. And A over B is a way that we can write a ratio. But again, the rule is that B cannot be equal to 0. The reason being is that when you write a ratio like this, it's really another way of writing a fraction. And 0 cannot be in the denominator. We've discussed this for quite a while now, because you make it, any fraction is a division problem. You make this into a fraction, you can't divide by 0. So therefore, 0 cannot be in the denominator. We're going to look at a couple scenarios for this today, but before we do that, I'm going to try to recreate a little bit of the Venn diagram that you see on page 283. So here we go. I'm going to give it my best shot here. I'm not going to be able to do it nearly as pretty as they have it on the top of page 283. But you'll notice here I am starting with a very large box on the paper. And this box represents all rational numbers. Anything that can be written in A over B form. Now, it doesn't necessarily mean that it is written in A over B form. It just needs to be able to be written in A over B form. So, for example, we might have 4. Can be written in A over B form when I do 4 divided by 1. 4 over 1 is A over B form. I might have negative 17 and 2/3. There's a mixed number. It's a negative mixed number even. That can be written in A over B form. I'd have to make this into an improper fraction rather than a mixed number. I could have a positive mixed number and do it the same way. 3.5. As an improper fraction, 3 times 2 is 6, plus another half is 7, so that's 7/2. 7 over 2 is A over B form. I could have a negative 8. I could have a negative 17. I could have a 0. I could have a 0.7. This is a decimal. It is 7/10. I could write this as 7 over 10 and have it be in A over B form. I could have another fraction, 3 over 4, whatever it may be. All of these numbers that I have here can be written in A over B form. Almost any number that we're familiar with can be written in A over B form. The alternative to a rational number is an irrational number. There's not a whole lot of those out there that we work with on a regular basis. The most common one would be pi. Pi is an irrational number. There's estimates for pi that can be written in A over B form, but the actual number pi cannot be written in A over B form. Now, the next layer of this is all the integers. So you'll notice on page 283, there's a couple bubbles inside the Venn diagram. I'm going to make another box, but everything inside of this box also is inside of the rational number box. So everything that I've boxed up here would be known as integers, okay? So notice that all of the integers, every single integer, fits within inside the rational numbers box, but even though it is a rational number, not every rational number is an integer. So negative 8 is a rational number, but 3.5 is not an integer. And you might also notice that there is another layer that we can get to, and that would be these guys down here. And this would be whole numbers. Every whole number is also an integer. Therefore, every whole number is also a rational number. But again, it goes this way, it goes out. Whole numbers are integers and rational numbers, but it does not go the reverse way. Rational numbers are not necessarily integers or whole numbers. So that's just kind of a neat way of looking at it. Kind of become familiar with that. In example 1 on page 283, we see our first set of homework instructions. So you're going to have homework problems that look pretty much exactly like this. Different numbers, of course. And all that you're being asked to do is to prove that these are rational numbers by making them A over B form. Now, hint, first of all, they all are rational numbers. They all can be written in A over B form. So don't write on your homework, not a rational number, or it can't be done, or anything like that. All of these can be written in A over B form. And we're going to look at that right now. Now, one of these, -3/5, you might be saying that's already an A over B form, but it's actually not. A over B form cannot have a negative sign outside. That would be the opposite of A over B form. But there's an easy way that we can put this in A over B form. In fact, Mr. Lorenz already kind of cringes at the fact that there is a negative sign outside of the fraction. You should know by now that I don't like having negative signs outside of fractions. So that's kind of my sneak peek on this one. All we're going to do is kind of fix it to Mr. Lorenz's style. 6. I need to make this into a division problem that equals 6. And the easiest way when I'm dealing with whole numbers is to simply take my whole number and divide it by 1. I've just proven that that is a rational number because 6 divided by 1 is equal to 6. Easy. This next one, again, this is the one that you might be saying it looks like it already is in A over B form, but remember, you can't have a negative sign outside of your fraction. So all I'm going to do is put my negative sign in my fraction. -3 over +5 is the same thing as -3/5. Easy. Now, the next one, I want to point out that your book has a different answer than I would give for this one. Your book simplified this after they did the work. But nowhere in the directions does it actually say that you have to simplify these numbers. So you wouldn't have to. It wouldn't be a bad thing to do, but any decimal, and I think it maybe wasn't a wise thing for them to choose 0.75 because that's a pretty common decimal. But any decimal can be written in A over B form simply by reading it using the proper place value instead of saying 0.75. So what I'd rather do is I'd rather look at this and say it ends in the hundredths place value, and this number is 75. So this is 75 hundredths, 75 over 100. I've just written it in A over B form. Now notice your book, I will go the extra mile like your book did, but this would be perfectly acceptable. The directions do not say you have to simplify, but it would be a good practice to do. Your book is going to then say 75 can be divided by 25 3 times. 100 can be divided by 25 4 times, and I end up with 3 over 4. So just two numbers, A over B form, two A over B forms that are saying the exact same thing, which is 0.75. The last one is -2 1/3. All I'm going to do with a mixed number is I'm just going to write it as an improper fraction. So 2 times 3 is 6, plus 1 is 7 over 3. And don't forget this negative sign has to go with it, so that's -7 over 3. -7 is my A, 3 is my B. I'm done. Okay. Now in example 2, I'm asked to order these they are not integers, these rational numbers from least to greatest. And they did something that is really, I think, valid, which is use a number line. They used a number line to kind of help themselves out. And I'm going to do the same thing. And I'm going to look at this. I'm going to say First of all, before I even do my number line here, I'm going to point out that this is negative, negative, positive, negative, negative. 4 of these 5 numbers are negatives. 1 of them is positive. So even though 2/5 sounds really tiny, guess what? It's the greatest of all of these. I should know that right off the bat. That will just kind of be like a little helpful hint. I'm going to notice that this is the biggest one, so it's less than 1. So I'm going to make sure that I include everything that would possibly be in here. So I'm going to go all the way up to 1 on my number line. The smallest number is negative 1.6. That's negative 1 6/10, which is a little smaller than negative 1 1/4. Negative 1.6 has a little bit of a greater absolute value, so a little bit further away from 0 than negative 1 1/4. But it does not reach negative 2, so I'm going to have the bottom of my number line be negative 2. So I got negative 2 all the way to positive 1. I'm going to try to put, I'm going to try to make this even. And I did a decent job. Negative 2 to negative 1 to 0 to 1. It's a little uneven. This is a little bit bigger than this. But if you can please pretend that I did a great job, that would be wonderful. And then I'm just going to put a halfway mark between each of these. So this is halfway between 0 and 1 is 1/2. Halfway between 0 and negative 1 is negative 1/2. Halfway between negative 1 and negative 2 is negative 1 and 1/2. So that will kind of give me some points of reference. 2/5 is my biggest one, and it is not even 1/2. It's a little bit less than 1/2, so I know that it's going to be smaller than 1/2, and I'm going to put that one on there right away. I also know that I have a negative 1. That's a really easy one to mark on my number line. I already stated that my least number, or I guess, how do I want to state that? The smallest number that I have, the least that I have is negative 1.6. It has the greatest absolute value of all the negative ones. So it's going to be actually between negative 1.5 and negative 2, closer to negative 1.5, but just on that side of it. My negative 1 1/4 should be halfway between negative 1 and negative 1/2. And last but not least, which one am I missing? Oh, negative 3/8. Negative 3/8 is not quite negative 1/2. So it's actually going to be closer to 0 than it will be to negative 1. Not far from negative 1/2. And there's my negative 3/8. So I've got these now listed on my number line. If I do this carefully, I can use the number line to actually just have them nicely in order. And I'm going to write this down on my homework, negative 1.6. The next one is negative 1 1/4. The next one is negative 1, followed by negative 3/8. And last but not least, actually, of course not least, it's actually last but greatest, is 2/5. And there's my answer for my homework. Okay? Now, the next thing that I'd like to do is I'd like to point out the top of page 284. And I'm going to bring my page 284 to the camera here. And on page 284, you see what it's got a box here that's reminding us about the commutative property of addition, of multiplication, the associative property of addition and of multiplication, and how we can use these to make adding and subtracting numbers really, really super easy. Actually, really more adding and multiplying numbers really super easy. We really want to be familiar with these so that we can use them to our advantage in example 3. So just to remind you, A commutative property of addition and multiplication says it doesn't matter what order you do it in. 5 plus -6 is the same thing as -6 plus 5. They are both a -1. As far as multiplication, 4 times -7 is -28. -7 times 4 is also -28. Doesn't matter what order you do addition and subtraction in, or excuse me, addition and multiplication. Commutative property says it's going to be the same thing. Associated property of addition, associated property of multiplication is similar, but it says if you have grouping symbols, but all you have is addition, both in and outside of the grouping symbols, it doesn't matter what order you do it in. It doesn't matter what group the groups are. 9 plus 8 is 17, plus 6 is 23. On the other side, 8 plus 6 is 14, plus 9 is 23. It's 23 either way. Same thing with multiplication. 2 times 3 is 6. 6 times 4 is 24. 3 times 4 is 12. 2 times 12 is 24. Doesn't matter. Okay? So what's the big deal, and why does this even matter? Well, we're going to show why this matters in example 3. So I think I just knocked my camera a little bit. I'll just readjust here, make sure that I'm all on screen here. In example 3, I've got a couple problems that show up. The first one is this bad boy, -10.6, -10 6/10, however you want to state it. -10 6/10 plus 3 plus -4 4/10. How am I going to use the commutative property or the associative property to make this easy on myself? Well, I'm looking at this already, and I might be thinking back to the adding and subtracting of integers from a couple sections ago. And it was not fun adding and subtracting integers. It was so much easier just multiplying because we just had to remember if you're multiplying two negatives, it makes a positive. But a positive times a negative is equal to a negative. But unfortunately, we have a negative plus a positive and then another negative. So what I'm going to do is I'm going to know my rules of the commutative property, and I'm going to use that commutative property to rearrange my problem right off the bat. Instead of saying -10.6 plus 3, I'm going to have positive 3 plus 10.6, -10.6. And then I'm going to have a negative, I'm going to add my -4.4. And you see what I've done by doing this is I put my two negatives right next to each other. And if I know my rules for the associative property, it doesn't matter what order I do this in. I'm going to get the same answer. So I can actually use the associative property to add some grouping symbols in here and say, let's actually do this first. -10.6 plus -4.4. This is a negative plus a negative. And since they're both negative plus a negative, I'm going to have a negative sum. Okay? And everything else is going to copy down. 3 plus whatever my negative sum is going to be. 10.6, to add two negatives, I'm just going to add the absolute values. 10.6 plus 4.4 is 15. This is -15. So now I have 3 plus -15. And I only have to worry about my negative plus a positive one time. I only have to do it once. And so I'm going to look at this, and I'm going to say 3 plus a -15. My rules for adding a positive and a negative is subtract the absolute values. 15 minus 3 is 12. And then you're going to keep the sign of the absolute value that was larger. So my -15 had a larger absolute value than my positive 3. So this 12 is going to be a -12. And there's my answer for example 3B. Okay, lots going on there. I used the commutative property, I used the associative property, and then I just recalled some of my rules for adding and subtracting integers. Now, example 3B is another one. This is a multiplication one. I have -25 times 7 times -4. This may look like a little bit of an intimidating multiplication problem, quite frankly. But if I know my rules for the commutative property and the associative property, it is actually a super, super easy problem. okay? I might be looking at this and saying, oh, negative 25 times 7. Well, I would want to go to my calculator for that. Negative 25 times 7 is negative 175, and then I got to do negative 175 times 4. Well, guess what? Let's use the commutative property instead. Instead of doing all that kind of stuff, let's use the commutative property. By the way, these steps, if you get this down really well, you can be doing this in your head. Negative 25 times negative 4. I'm even going to put negative 25 in parentheses just for safe measure. Times 7. And the reason why I've done this is because then I can put some grouping symbols around these two. Negative 25 times negative 4. That's a negative times a negative. Those are the only two negatives in this whole problem. A negative times a negative is a positive. And 25 times 4, that is a problem. That is a mental math problem. 25 times 4 is 100. So this is going to turn into 100 times 7. 100 times 7 is a piece of cake. That is 700. Again, this whole problem from here all the way down, this is all mental math. If you know your properties, this kind of stuff can be done just like that in a snap. You don't have to be dinking around with anything. I've got a couple more problems that I'd like to show you. And these go along with example 4. But before we do example 4, there is another box that reminds us of the additive inverse and easy for me to say. The additive inverse and the multiplicative inverse, as well as the additive identity and the multiplicative identity. The additive inverse simply states if you add the opposite of a number, you get 0. The multiplicative inverse says that if you multiply by the reciprocal, you get 1. The additive identity, if you add 0 to any number, you get whatever number you started with. Negative 7 is plus 0 is equal to negative 7. The identity property of multiplication states that if you multiply any number times 1, then you get whatever that number you started out with. Okay, so I've got a couple examples where I'm going to use either both the additive inverse and the additive identity, or the multiplicative inverse and the multiplicative identity. Let's start with this one. I'm first going to use the commutative property to put 2/3 plus negative 2/3 next to each other. Again, by the way, this whole problem can be done in your head if you are familiar with these properties. 2/3 plus negative 2/3 is equal to 0. Zero plus 7/10 is equal to 7/10. And again, all of this, if you know your properties, I wouldn't be writing this down. If you know your properties well, this is mental math, and you can look at this right off the bat, identify that this and this are going to cancel each other out, leaving you with nothing but 7/10. So it's a very advantageous thing to use both the commutative property in your head. I used the additive inverse to say that 2/3 plus negative 2/3 is equal to 0. And then I used the additive identity. 0 plus a number is whatever that number started out as. So all of those properties are being present in this one problem. I've got one more problem here. 1/3 times 5/6 times 3. I'm going to again use the commutative property. This time I'm going to use the multiplicative inverse, and I'm going to use the multiplicative identity. 1/3 and 3. If I see a whole number and that same number shows up in the denominator of a fraction, that is a telltale sign that those two want to be right next to each other. So I am going to use my commutative property. Again, this is all in my head. All this blue is in my head. 1/3 times 3, and I'm going to write it like this on purpose, times 5/6. Okay? And I wrote it like this because actually 3 is the same thing as 3/1. We wrote that like that as a rational number earlier. And when I have 1/3 times 3/1, this makes reciprocal. This is the multiplicative inverse. 1 times 3 is 3. 3 times 1 is 3. 3 divided by 3 is 1. These two fractions multiplied together are equal to 1. This is the multiplicative inverse. A fraction times its reciprocal is equal to 1. So I'm left with 1 times 5/6. And now I have the multiplicative identity, which states multiply any number times 1, and you get whatever that number started out as. So my answer to this is 5/6. And I should be able to recognize that. Again, this is all mental math. I would not be writing this down on my paper. But that's because I know my properties. If you know your properties, this can all be mental math. You can look at this and say 1/3 times 3, that's 1. 5/6 times 1 is 5/6. And it's as simple as that. So it's very, very important that you do know your properties. All right, ladies and gentlemen, the last thing I have for you is your homework assignment. I want you to do page 286, starting on page 286, numbers 14 through 24. Again, remember that the directions for 14 through 17 are simply just write it as A over B form. You're going to have to do a little bit of putting things in order, and then a few more where you're going to have to do some evaluating the expressions. Look for those scenarios that we just went over. Every one of these problems has something in it that you should be kind of looking out for that will make it an easier problem to do. So you might have to use the commutative property or the associative property or something, but there will be something in there that will make it an easier problem to do. Thank you very much. Have some fun.